Hello everyone. Welcome to this mini lesson on applications of the mean value theorem. You'll remember that's what we've been talking about the last class we met together, and these are specifically real life applications of the mean value theorem. So if you think about what the mean value theorem has told us and what we talked about in class, assuming you have a function that's continuous on the closed interval and differentiable on the open interval, there's going to exist a c value in the interval from a to b, so that somewhere the value of the derivative at a certain point on the curve is going to equal the slope of the line that connects the endpoints. So if you think about how this would relate to real life then, all right, think about the derivative. We've learned that as instantaneous rate of change. Right, back in when we started talking about the derivative and applications of it, you'll remember that's really how we talked about it. It's an instantaneous rate of change, the rate of change at one particular point in time. F of b minus f at a all over b minus a, remember how we talked about that as an average rate of change. So really what the real life applications of this, and I mentioned this in class the other day, is that what the mean value theorem allows you to do is for any real life situation that can be modeled by an equation, you can find that point in time at which the instantaneous rate of change is equal to the average rate of change. This is going to be over an interval, remember. So like over an interval of time. And remember, our instantaneous rate of change is going to be at one particular point in time. So what I have for you here are three different examples of different types of real life applications. All right, so the first one goes back to a problem that we're pretty familiar with, dropping an object from a height. So suppose we have an object that's being dropped from a height of 500 meters and its position function is modeled by the equation negative 4.9 t squared plus 500. So part A is a problem we're pretty familiar with. All we want to do is find the average velocity of the object during the first 3 seconds. So, as we've done lots of, we'd simply calculate s of 3 minus s of 0 over 3 minus 0. When you do the subtraction in the numerator, I know you come out with like a negative 4.41. You can try that later on your own. Divided, of course, by 3. So we come out with a negative 1.47 about. And that would be meters per second. All right, something that we're pretty familiar with, just exactly like we did before. So that would be the average rate of change. So we're going to need that value and come back to it to answer part B, which you see here. All right, so what we're going to do now is use the mean value theorem to verify that at some point in time during the first 3 seconds of fall, the instantaneous velocity equals the average velocity. Well, we just calculated the average velocity. Remember what our position function was. This is what it was given to be. So if we calculate our velocity, remember our velocity is given by the derivative of the position function. That gives us a negative 9.8t. So what the mean value theorem says is that someplace the average rate of change, all right, that's the negative 1.47 that we calculated before, is somewhere going to equal the instantaneous rate of change. So all we do is simply set that equal to the derivative we found. And that's easy to solve for t, and you get 0.15 seconds. So what this is telling us is that for this particular object, when it's falling, at 0.15 seconds, the instantaneous rate of change at that particular time is equal to the average, from 0 seconds to 3 seconds. So that's a typical type of mean value theorem related to the position function of an object. So the next one I have is more of like a, business application, I guess you could call it. Suppose we're talking about a company introducing a new product, and they're going to sell S units of them. The function for the number of units sold is that 200 times the quantity 5 minus 9 over 2 plus t, and t is the time in months. So the first thing we're asked to do is to find the average value of S of t. So what's the average number sold during the first year? So obviously that's years, or months rather, 0 to 12. So we're going to have to calculate S of 12 minus S of 0. Of course, feel free to do that in your calculator. Over 12 minus 0. And I think I actually have it set up here. Let's see. All right, so I would probably just put the equation that models how many were sold under y equals. Then you can just do a table if you want. I think I got to set up my... Now another thing you could do, which is even easier if you want, there we go. You could do like y1 at 12. If you just want the calculator pretty much to do all your calculations for you, minus y1 of 0. I get that. That's the numerator, divided by 12. Guess it doesn't want to do the decimal. Interesting. Let me try this. Doesn't really matter if you do a decimal or a fraction. It wouldn't matter. There we go. So that would be the decimal equivalent of it. I thought that would be easier since we are talking about, time and how many units sold. Maybe a decimal kind of answer is making more sense. So what this is telling us is that over that first year, on quote-unquote average, 64.286 units per month were sold, because this equation does model the number of units that were sold in months. All right, so while you're here, you might want to store that because we are going to need that. So I'm going to store that as A. And then we'll come back to it in a second. All right, so let's go back to the PowerPoint. All right, so what we just found was that S of 12 minus S of 0 all right, that was about 64.286 units per month. Okay, it's units per month because the numerator would have been the number of units. Denominator would have been the time in months. That's why it's units per month. All right, so if we take a look at part B, Now we want to know during what month would the derivative equal, sorry, I can't type, the average value during the first year. So again, that's your application of the mean value theorem. So what the mean value theorem is telling us is that there should be some point in time at which the average number sold is going to equal the instantaneous number that's being sold. All right, well, the instantaneous number sold is what's going to be given to us by our derivative. And the average number sold is what we just found before, that's 64.286. All right, so this is something we could solve on our calculator if we wanted to do that instead. On the AP exam, as long as you would be showing that you're setting your derivative, whatever that is, equal to that 64.286, that's fine to let the calculator do all the work. All right, so let's go back to the calculator. All right, and under y equals, we had our equation, remember. So if we go down to y2, let's tell y2 to be the derivative of that y1 function. So remember, you do that through math 8. And we want the derivative of what we have under y1. And you're going to do x equals x, because remember, you want the graph of it. Now the other thing you might want to do is turn off the graph of your first equation. All right, so it should look like that. Remember, there's no black box on top of the equal sign for y1. That's how you know it will not graph for you. All right, now what we want to set that derivative equal to, though, is what we have under what we stored, that 64.286. And remember, I had stored it as a. So you can type in there whatever you had stored it as. Okay, so once you have that set up, maybe it's easiest if we perhaps do maybe zoom fit. See if that'll do any good, if that gets me anywhere. So that's the graph of the derivative. And I think that little line all the way down there is the line that's 64.286. So let's check out our window. We might have to play with it a little bit. Yeah, I mean, if you take a look at this, our x's might be okay, -10 to 10, but check out the y's. I mean, we know we need a horizontal line up as high as 64. I mean, this is going up to 248,000, so we probably don't need it to go quite that high. Let's maybe do it up to like 75. You know, and if you want to kind of just change this, maybe make this 10 if you want, or something like that. And just hit graph, see if that gives us anything better. There you go, that's much better. The part over here that you see to the right of this boldface vertical line, the boldface vertical line is your y-axis. So, you know, time can only be positive. So we are only looking for the answer in the first quadrant. So if we trace and find that point of intersection, you can see how high right now your spider would be, up at 450. So if you just kind of start hitting your right arrow, I usually don't go too fast because then I miss them going by. Ah, there he is. So we can probably run our intersection from there. All right, so give it a try, and hopefully you're coming out with approximately 3.292. So it's at that month, so what, March, January, March, sometime in March, that we know that the average number of units sold would be equaling the instantaneous for that month. So it would be in March that the number of units they're actually selling in March, that 64.286, is equal to the average for the entire year. So as you can imagine, if you're the owner of this company, you know, and maybe from past history, you're able to figure out the average number that you sell over the course of a year, you know, it would be beneficial to know, okay, during what months are you actually producing that number? you know, there's some really good production kind of manufacturing questions that can be answered with that. So that's why this would be really valuable information for a company. All right, so we have one more to go. Go back to the PowerPoint. So a more environmental problem, dealing with the growth of a red oak tree. The growth of the tree can be approximated by that cubic function you see there. G is the height of the tree, and T is the age in years. And notice T has to be in between 2 and 34. So if this ends up being something we're going to do on our calculator, that's something we can kind of keep in mind as we set up our window for the x's. So the first thing we're going to do, we want to find the average height between the tree being 20 years old and 34 years old. So we're trying to find G of 34 minus G of 20 and this is definitely one we'll want to put that cubic equation under we can replace the other one we just finished with this one. Now, I would highly recommend just doing this, crunching the numbers in your calculator. You can try it later. It should come out that I think it's approximately, perhaps it's exactly, but 1.148 feet. Now that's how much it grew, okay? Because it's the growth of the tree, okay? So don't think the tree is only 1 foot tall, okay? This is how much it grew over that time, okay? So maybe this should be like average growth in height. Perhaps I should have worded it that way instead. All right, again, the tree is not just 1 foot tall. It grew that much. All right, so you can probably guess what the next question is going to be. Is determine the year in which the tree's growth really. Oh, good. There we go. Equals the average height over the age 20 to age 34. So that's what we just figured out. This is another one you could let the calculator do the work. You could easily solve this graphically if you'd like. Okay, I got red. Okay. We could find, it's very similar to what we did before, we could let the calculator graph the derivative and find where that's equal to 1.148. All right, so if we go back to the calculator, and go back to y equals, let me clear out what I have under y1, and we'll type in and I'm going to get rid of what I have under y3. If by chance you had stored that 1.148, that would be fabulous. And I'm going to go turn off y1. So it looks like that. Now this is where we could take advantage of the fact that we know our y's don't have to go up that high, because remember our intersection is only going to be up at like a y value of 1.148, so we don't have to go too high on the y's. We could just go under our window and kind of play with it from the last one. And remember, it was only good for t-values of in between 2 and 34. So that might be good to let our x's be that. And maybe just do a y of 0. I don't know, maybe up to just 3 or so. It doesn't sound like you have to go too high. Let's see how that looks. So there's the graph of the derivative right there. Makes sense, it's a parabola. And notice how we do get 2 answers for this. That's one reason I like this example. We've talked about with the mean value theorem, you can get multiple answers on occasion. This would be an example of that. All right, so we'd want to find each of these intersection points. All right, maybe I'll go find this one on the right first because I'm kind of closer to that. All right, so it's at year year 27.674 years old, at which the growth in height is going to equal the average over the years from 20 years to 34 years. That's one time. Notice what the other one is. Let's go find the other one. All right, and the other one's just a little bit more than 2 years, 2.770 years old. All right, so in this case, this tree has 2 ages at which its instantaneous growth, amount of growth, is equal to the average over the time period of 20 years to 34 years. So hopefully this gives you a good idea of different types of scenarios. We've given you a environmental, biological kind of example, a manufacturing production type of business application, and then the one that we started with, the object motion and a position function. So 3 very different examples, but you can see they're pretty much all done the same way. In each case, you're just adhering to what the mean value theorem tells us, is that someplace the instantaneous rate of change, the derivative, is going to equal the average rate of change given to you by the slope of the endpoints.